Welcome to Public Affairs Public Access. I'm George Reiter. I'm a professor of physics at the University of Houston, and I do a radio show on KPFT called Thresholds at 6 a.m. on Thursday mornings. My role here is as host for a conversation with David Criswell, professor emeritus at the University of Houston. Professor Criswell had been the head of the director of Institute for Space Systems Operations at the University of Houston. He has been working since the 70s on issues around the way in which we might make use of the moon for human purposes. Dave, welcome to Public Affairs Public Access.
Well, thank you very much, George. Pleasure to be here.
The topic tonight is about making use of the moon to provide power for the Earth. Power on a scale that would be sufficient to provide for every member of the world community, which you're figuring will be about 10 billion people. Is that right, Dave?
That's what I use just to scale
right.
the engineering. It could be much more.
Right. At the level that the United States has it now, without destroying our environment in order to provide that energy. Dave will be presenting for you the outline of how one does that. And we'll be interacting as we go forward with that. So Dave, perhaps you would begin with the presentation.
Okay, we have a real need to change over to a completely sustainable form of energy. And over the past 35 years or so, it's shown, at least to my conviction, that probably the only way we can do that is to capture sunlight on the moon and change it into a form we can transmit down to Earth and collect very efficiently as we need it, when we need it, and then output pure electricity that would have essentially no environmental downside. And this system is called the Lunar Solar Power System, as shown on our title slide here. And as far as I can tell, it's our only reasonable option to have sustainable global wealth, which could just vast increase in wealth compared to what we have now, and we could just keep generating it as long as the sun is there and the moon is there. And to appreciate it, I think it helps to compare, or to very briefly review how we do things now. And it's very different. Now we produce our electric power, and that's what I'll be talking about tonight. We produce it by burning carbon fuels, primarily coal and then natural gas, and a little bit around the world petroleum. And that accounts for probably 80% of all the electric generation in the world today. And if you average over our almost 7 billion people now, we produce less than 1/3 of a kilowatt of electric power per person. What we need, though, is to get up to 2 or 3 kilowatts of electric power per person, and that would let us get all of our resources out of the common resources of the crust of the Earth, the oceans, and the biosphere. And that's a real challenge. Now, the way we do it today is we get the coal, transport it over thousands of kilometers to power plants. We do the same thing with natural gas. And we ship both natural gas and oil, both in pipelines and with ships. We bring them to very major power producers that are spread out over the entire world, probably the order of 25,000 power plants. And at each of those plants, we convert those fossil fuels into, burn them with the atmosphere. And we're now releasing on the order of several tens of billions of tons of CO2 every year into the atmosphere. And that rate is increasing. And this is a huge movement of mass around the Earth. This is probably, from an engineering standpoint, the greatest amount of mass flow that we do around the Earth. And it approaches that scale of actually the geologic movement of mass.
You mean tectonic plates?
Yeah. Mm-hmm. If you look at the total amount of mass that the geothermal energy of the Earth propels, we're up on that same scale.
You mean the amount of, let me just get that straight. So
Sure.
the amount of mass that we're using in terms of to produce up the power for our societies throughout the world is being moved, that's comparable to the actual motion of the continents, the drift of the continents. Is that correct?
Yeah, basically, and including volcanoes and all of this. And it's the power levels are actually getting to be similar. For years I'd been estimating or using estimates that the total geothermal heat output of the Earth was about 35 to 40 terawatts. A terawatt is 10 to the 12th watts.
So that's a billion watts.
No, it's a million billion, 10 to the 12th.
Oh, that's right. It's
Yeah.
a million billion watts. That's right.
And that figure may be as high as 45 terawatts. And that's what drives the continental drift. It's what drives mountain building, all of this. And we now operate at about the 15 to 16 terawatt level in the production of commercial energy, both thermal energy and electricity. About a third or fourth of the total energy that primary energy gets converted into electricity. And the way China and India are growing, we're not that far off actually from producing it. We're within a factor 2.5 now of producing as much commercial energy around the world as the entire Earth releases as geothermal energy.
And if in fact the project you're talking about bringing solar power from the moon was implemented, what kind of energy level, what kind of energy usage would be having then when everyone in the world had sort of access to electrical power at the same levels that, say, the United States has now?
Well, the U.S. has, okay, that's a fair estimate. That's that last bullet. We need on the order of 2 to 3 kilowatts of electric per person to give the same level of prosperity as present in Western Europe or Japan now. And what we need to do is to find another source of that electricity that does not involve moving these enormous amounts of mass around the planet to do it, because you don't get much energy out of a given molecule of carbon. In fact, that's an interesting thing. Carbon itself does not release much energy. Carbon, hydrocarbons and all, under most conditions are inert. If you go back to the start of the electric age, oil-soaked paper and cloths were used for electric insulation, and it all worked okay until you got a spark, and that spark had access to oxygen in the atmosphere. And when we produce this electricity burning coal or oil, what we're actually doing is just using the carbon as a fuel. The actual energy comes from the free oxygen, chemically free O2 in the atmosphere. And so we think of ourselves as an oil-powered or a coal-powered modern society, but we're actually a free oxygen-powered society. And what we're doing, we do live on a spaceship Earth, and what we're doing is burning our oxygen to keep our society going. And we actually, the tonnage of oxygen that's absorbed or used in that process every year is about twice as much as the tonnage of the carbon fuels, hydrocarbon fuels that go into making it. And so, in a way, the hydrocarbon fuel system is actually an example of solar energy. The carbon, the ancient carbon, came from the creation, the separation of oxygen in CO2 by photosynthesis, driven by solar energy. And it takes about, a given oxygen atom lives in the atmosphere for about 5,000 years. And this process has been going, oxygen generation has been going on for about 500 million years. And so we've been through that cycle about 5,000 about 10,000, let's see, 500 million divided by 5,000, about 1,000 cycles of generating oxygen. A piece of the carbon gets stored and the oxygen gets reabsorbed in rocks and all. And there are estimates that we have enough, most of that carbon was lost, but there are estimates that say between 15 and 20 of those cycles of carbon is actually stored in the form that is called kerogen. It's just black, or not black, but brown gunk. Coal is the pure end member, and then stuff that is just the color of carbon in soil is the least. And there's a good chance that the very, very smart people in the petroleum industry can extract economically from the crust of the earth enough carbon to essentially burn up our present oxygen atmosphere. It's a long way off, but it's not out of sight. The real point...
In the meantime, we have the immediate problem of the CO2 levels rising.
Oh, the CO2 will be far, far more important. But I think the thing here is to try to get a clear mindset that we really do live on a spaceship Earth and what to do about it. And so what do we really need to do to get a sustainable power system? Well, we've got to eliminate, in fact, let me go back here and I'll just mention these points while you're looking at the figure. First thing you've got to do is eliminate the fuel gathering in this picture, and its transport and its burning. Eliminate the CO2 production, perhaps even reverse it, and eliminate all of those costs that we introduce into this by having to move all that mass continuously through the biosphere. Eventually, we'll be able to eliminate all these terrestrial power plants by tapping usable solar energy directly on the moon and sending it down. And that means eliminating their ancillary cost of the facilities, cost to maintain them and build more. And we've got to provide this energy in a way that it's really independent of the biosphere, so that we can have control over our own destiny regardless of what the biosphere does to us, including big natural events, super volcanoes or asteroid impacts or that sort of thing. And so our challenge is to provide sustainable carbon-free energy. If we have that, then we can get all of the stuff that makes us materially rich right out of the crust of the earth. Mines become almost non-important. We'll have the energy to recycle all of our goods and our water, our agricultural chemicals. And we can conduct all of the stuff that's important to a healthy life, like agriculture, industrial production, residential power, transportation, all with no impact on the biosphere we live in. Now, we actually should be, I'll get into this more later, but if we'd stayed on the moon during the 70s, I think we could have started this power system in 1980 and the U.S. would now be powered by it. But we're here today. We've got to get back to the moon to make this work.
But the technology existed in 1980, you're saying?
Yes, yeah. And it's only gotten better since then. Not only the technology to operate the system, but to produce it on the moon. So if we're looking at the scale that we've got to go to for 10 billion people, which probably will be 2050 or 2060, you take 2 kilowatts a person, you multiply it times 10 billion people, and that's 20 terawatts of electric power. And today, we only produce about 2.1 terawatts of electric power, 2.5 worldwide. So it has to be a huge increase. But one of the things that's not generally recognized is that the wealth of a nation is directly proportional to how much electric energy it uses every year. And when you go into Department of Energy and the Department of Commerce data on the energy used by all countries in the world and what they produce in the way of goods and services, you find out that the world, or Western Europe and Japan, produce about $42 trillion of new product every year by using 1 terawatt electric year of electric energy. If you brought the entire world up to that standard of efficiency of use of electricity and you had 20 terawatts, that means the gross product of the world could exceed $800 trillion a year.
Which is how much per person?
Well, that turns out to be about $80,000 per person of gross product.
So let me understand if I get what you're saying, that although there are different ways one can use energy, that in the end, the amount of production of useful goods and services that are produced turns out to be proportional to how much electrical power that you've been using.
That's right.
So you can essentially project the wealth of a future population on the basis of how much electricity they have available to them.
Yeah.
And you're saying that with the kind of power that could be beamed back from the moon, and we'll get to that in just a minute about how to do that, you could have a level of wealth corresponding to about $80,000 per person.
Yeah.
Per person, not just for, you know.
Not a family, a person.
not just for fairly wealthy people here in the United States, but throughout the world.
That's right. And according to the CIA database, last year, the world average was about $9,000 a person. Right. Gross world product per person. That's not how much goes into your pocket, because a lot of that goes into maintaining the society. So essentially, with this option, you can just dial in the amount of wealth that you want to have. The way to do it is the lunar solar power system, and this figure, which I'll talk to, but I'll read my bullet points here so you don't have to read them on the screen. The sun's the ultimate source of all of the power. It's paid for. It's good for at least 4 or 5 billion years. Right. You don't have to maintain it. So all of the cost you usually associate with conventional power systems here on Earth, both carbon and even nuclear power or even solar, you don't have if you just can figure out how to more directly tap the sun. So the basic idea is that the sunlight falling on the moon is totally predictable. The moon has no atmosphere, and it has a day-night cycle that's 27 days in Earth days in extent. So you've got to build bases on the 2 edges of the moon and some supplemental bases around the edge as seen from the Earth. And then you can have power coming back or on one of your bases all the time, every year, except for an eclipse of the moon by the Earth, and that lasts about 3 hours, so you can plan for that. On the moon, solar arrays built out of the lunar material will capture a few percent of that solar power, change it into beams of microwaves. It's essentially just a big form of radar, and those microwaves can come down to Earth through the atmosphere and into what's called a rectenna, which is essentially a huge field of solid printed circuit rectifiers, and changed into electricity at about 90% efficiency. It makes sense economically if that beam is only 20% of the intensity of sunlight. And so you could walk into it and you'd feel warm, but that's about it. It would be coming down, though, into an industrially zoned area, fence around the rectenna, so only workers would go inside and they would wear protective clothes if it
How about, you know, sort of fringe fields on the edges spreading out? I mean, people are concerned about the radiation from microwaves. Is there some biological effect that we would have to watch out for in this case?
The fringe fields, one of the really major advantages of beaming from the moon is you can make the transmitter's area very, very large. And that means you can have extremely great precise control over where the beam goes and how much energy goes into the primary beam. And the for a 20 terawatt world, you're actually delivering that much electricity to consumers. The fringe field would have an intensity less than that of the light of a full moon. In other words, it would be orders and orders of magnitude down, immediately walking outside of the perimeter fence.
Right.
And it would essentially fall down to a very, very low level. And probably beneath the level that you and I are radiating microwaves at each other as black bodies, as heat animals, or the walls are radiating to us. So as far as I can tell, it will be safe, and it would also be extremely reliable that you'd choose a frequency of beams or wavelength about 10 to 13 centimeters, the industrial microwave band, to which clouds, rain, smoke are virtually transparent.
How about the total heat flux coming in from the moon? It's 20 terawatts. That's roughly half what you were saying was the sort of heat flux emitted by the Earth because it's got a hot core. Mm-hmm. Is that something you have to worry about?
Well, it turns out if you work at low power beam density, you don't. The beam coming in is converted about 90% into electricity, and that would go out over an enormous area to all the users and be
right.
and be released as waste heat, which infrared, which could just go back out into space. The surface under the rectenna could be painted white or covered with white gravel or something like that, because 90% of the sunlight can go through this sort of chicken wire.
Right, so the microwave beams get stopped, but the sunlight goes right through.
It goes right through.
Right.
And averaged over a year, you can reflect as much low-quality sunlight back out to space in total energy as the microwaves coming in. So this can actually be neutral. And it uses just, you could obtain this 20 terawatts from about 100,000 square kilometers of these rectenna areas. It wouldn't be all just one big rectenna. These would be located all over the Earth. And they would occupy probably a 30th to a 100th of the area if you were trying to do the same thing with solar cells, solar arrays on Earth.
Now, why is that? I mean, you're talking about actually building solar cells on the moon out of the material on the moon.
Yeah.
Why not just build them out in the desert?
Let's ask it the other way around. Why is it so hard to have successful large-scale photovoltaics? We don't at this point. Google just closed its program this past week.
Is that right?
Yeah, to try to use photovoltaics for its power centers. You're sitting there in a big field that could look like this rectenna, but it's covered with a solid cover of photovoltaics. And you have no control over the level of the sunlight that comes in.
Right.
You have no control of it at noon or in the evening. It goes away at night. With this system, you can bring the power in as you need it, day and night. And so immediately that means the solar array, the rectenna, is that much more efficient than a solar cell.
Right.
Also, you get something on the order of 90% conversion efficiency of the incoming beam, microwave beam, as compared to now less than 20% efficiency, in the real world less than 12%. What do you do when clouds, rain, fog come along? I remember once being on the skiing in Aspen, and I was a private pilot back then, and wanting to fly back to Houston, and I realized that the East Coast, from the Rocky Mountains east, had been cloud covered for 6 weeks. And we have, so what do? You build another array over in the Gobi Desert or in the Australian outback, and people have actually modeled that. And what they find is that by the time you build the power lines and the power storage, and these encompass the entire globe.
Right. Which you need in order to have reliable power. You're going to hope there's some sunlight somewhere.
sunlight
Right.
somewhere.
And you have to build each one of these things bigger because you're not sure what fraction of the time you're going to have sunlight.
Well, that's right.
Right.
And when you start putting all of these absolutely realistic constraints in, you find that rather than 100,000 square kilometers of rectenna, you would need on the order of 3 million to 7 million square kilometers of high efficiency solar cells.
Right.
And even then, you wouldn't know if you had dealt with the worst possible case. The rains in Australia last year could have taken all of those units offline for weeks. Sandstorms in the Sahara can do the same thing. And the problem is we're living inside of this biosphere which can just stop sunlight. And also it's a big planet. You're 24,000 miles around, and so when you try to distribute power, it takes massive power distribution systems.
And all the losses associated with going over those distances.
That's right. We're trying to get into the 21st century with essentially late 1800, early 1900 electric engineering technology.
Right.
And then you think of all the opportunities for terrorism to shut down major or all parts of the system. It would really be good to bring this in from outside. So this is what time is it?
Well,
Probably
it's
talking
about half
too
past.
much.
No, you're doing just fine.
Okay, yeah, we're actually halfway through. And so this is this is another view coming in a little closer. We've got the sun over in the upper right-hand corner here. And you can see bases on the bright side and on the dark side of the moon. And these bases would project power beams either directly to Earth, the side facing the moon, or when you're trying to get to the side of the Earth away from the moon, these beams would go through redirector satellites.
Are those a significant expense for the whole system?
They shouldn't be. They can handle, they would be on the order of 3 or 4 times the mass of the space station, and on the order of up to 1 kilometer across. But they would be, they could be microwave reflectors, or they could be a technology called reflect array microwave systems, in which it's a set of integrated circuits that can accept an incoming microwave beam and then put out multiple independently targeted beams out of that. And those are going to be very lightweight systems. It'll take a large transportation fleet to get all of this up, but it will be one that will be justified because of the payoff for it.
And again, the payoff for it is essentially power for humanity for the indefinite future at a level which ensures for every person on the planet the kind of a lifestyle that would be provided by an income of $80,000 a year.
Yeah, to start with.
To start with, right. Yeah. You could always make more.
Well, we've learned the progress over the past century has been, economically, has been in getting more and more efficiency out of electricity. Western Europe and Japan get this $42 trillion per terawatt electric year. The U.S. operates at the world average, about 60% less than that. Most of the developing world operate at about $12 trillion per terawatt electric year. And if you look at the rapid growth of China, it's directly proportional to how many coal-fired electric power plants they put in, and their dams. But they're far, far away from the amount of electricity they need. They need about 2.6 terawatts of electric power. They need, for their 1.3 billion people, they really need all of the electricity that the world produces to achieve the standard of living in the U.S. And they're a long way from doing that. So the question is, what do you do on the moon? And this next slide will focus in on a tiny little section of one of those white areas on the moon, on the 2 edges of the moon. And those white areas to our, this is overscaled just to bring out the bases, but the base needs to be, look to your eye when you're looking at the moon, on the order of 30 to 100 kilometers across. And what you would see in that base are thousands and thousands, tens of thousands actually, of power plots. And a power plot, and let me shift over to a talking sheet and I'll just leave the figure up there. We're on the edge of the moon, we're looking toward the Earth, and the Earth stays fixed in the sky there. It moves around about twice or three times its diameter, but it's a very slow movement over the lunar day. And it stays there day and night, as seen from that place on the moon. So that means if you put in a radar transmission aperture, it's basically looking at you all the time,
right,
where you're the Earth now.
And you can easily shift it around in order to focus on one of these satellites, for instance, or
follow a
right,
city going across the
right,
face of the Earth.
Right.
Now, what do you do on the moon? And what you do is build power plots. And a power plot's composed of solar cells. That's indicated by that number 1 on the slide. It's made, those cells are made out of the lunar materials by the machinery, mobile machinery and fixed machinery that takes the lunar soil and changes it into ultra-thin glass, extracts silicon from the lunar soil.
So these are machines which basically suck up lunar soil and extrude photovoltaic panels.
Yeah, that's right.
Yeah.
They also, it would be more like a road building crew here, right, than it would be a big monolithic factory. And you'd want thousands and thousands of these production sets up there. But that means the model, the core, the example production set of equipment can be demonstrated on Earth, like the lunar module, the lunar rovers, all of the stuff we took to the moon was demonstrated. Right. And you would have plenty of chances to revise it. It's an industrial operation. But what they would do is make the solar cells. They would extract either iron or aluminum from the lunar soils and make wiring to collect over a small area, say maybe the size of a football field, the photoelectric current, the power, and deliver it to a set of microwave transmitters at the earthward side of the power plot. Those transmitters then would have, it could be a technology as basic as the magnetron in your microwave oven. Or it could be now it could be more advanced solid state, but the magnetron's pretty efficient. That then, under computer control, sends a little sub-beam to the panel number 3, which is a screen wire reflector made out of lunar soil. It's fiberglass. Fiberglass tubes and fiberglass fibers that are coated with metal, and that panel then will reflect a subbeam back toward Earth. Now, if you think back to this white area, one of the lunar bases, what your eye would see, these power plots would be too small to see, but the thousands of them would be arranged around the curve of the moon so that they would look like they overlap into one huge transmitter. So it's a fully segmented phased array transmitter. And it would take about 100,000 tons of material in the form of these reflectors to send a beam back to Earth that could be focused as narrowly as 200 to 400 meters across.
And there's enough iron and other materials up there. We know that that's the case in the soil that's easily accessible?
Yeah. It's from the Apollo missions, the unmanned missions, and fairly extensive remote sensing. There's just no doubt that all that's there. I mean, we've actually had it in the labs here. During the 70s, I administrated the review of the first 3,500 proposals submitted to NASA from scientists worldwide to conduct far lunar research. And we knew within a couple of years, with great certainly by the end of Apollo 17, what was there. And then I had the good fortune of running a 3-year program on how you, toward the end of the 70s, on how you take the lunar soils and change them into engineering materials. And the stuff I'm talking about is from a real industrial engineering standpoint is completely doable, has been since the 80s. But going back to this overview slide, or I'm sorry, the base slide, you would replicate, you would build these power plots in hundreds of thousands of units and fill up one of those projection arrays, and by the time you're about a third of the way done, you have enough installed antenna surface area to start delivering commercial power to Earth.
And what would be the cost to get there? I mean, you've got to transport the factories up there. You have to get resources for people to live up there while this is happening. And this would take, to do that first, say, third, that would take you, what, 5 years, 10 years, something like that?
I built based on something like $25 million spent back in the 70s on constructing solar power satellites out of lunar material, out of terrestrial material, and an almost $1 million study by G.D. Conveyor back in the late 70s of building solar power satellites out of lunar material. I've been able to combine or modify those two into a systems engineering spreadsheet that lets me model that. And it gets down to how many kilograms of soil do you have to process a minute to get a certain production rate. And what I have, when I take 20 terawatts as a goal, I have a 10-year R&D program, and then a 8-year emplacement of the prototype, which is suggested here. And that prototype, the construction of the prototype, would allow you to get up to about a half a terawatt beam back to Earth, enough to meet most of the U.S. power needs, or most of them.
Approximately a quarter of what's being used right now by the whole planet.
About an eighth.
An eighth.
An eighth. 2 terawatts versus quarter terawatt.
Yeah.
And at that point, about 2 years past the half a terawatt, you would have, selling electricity at 10 cents a kilowatt hour, you would have paid for all your investments to that point. And that would be about $500 billion.
So $500 billion, which is less than the military budget of the United States, would, within a period of about 18 years, provide the beginning levels of power, and within another decade or so, you'd have it up to
20 terawatts.
20 terawatts.
This really is a case. You remember the old joke, if you want to have a baby in 9 months, share it between 9 women. Well, this is, they all just gestate quite a bit faster. It may be hard on the baby. But in this case, you can actually do that. You can simply put, as you gain complete confidence in the operating system, you can simply put many, many more of these production machine units on the moon, transmit them or transport them from the Earth. The other thing, though, is that with beneficiation, with selective sorting of lunar soils and in various ways, if you selectively sort by about a factor of 10, you can get the full range of materials you need to support a modern society, except for carbon. You don't need the carbon in the vast quantities we use it today. So what that means is you can start building a large fraction of your production machinery out of the lunar material, say 90%. And I'll get to this in just a minute, but that means then that you can start a growth of all of these power stations almost like bacteria growing in a petri dish.
Right.
The production process can go up, machinery can grow exponentially. That means the in-place power can grow exponentially.
And so it's gotten freed from the need for transport back from the Earth to the moon.
That's right.
Right.
But then there will be very good things that happen. Back in the 1700s, was when the magic cycle of being able to make good iron shifting from charcoal to coal, and then learning to make steel, making steam engines, making rails, and all of a sudden this whole thing became a very positive growth system. We can do exactly that same thing in the Earth-Moon system by establishing industrial production on the moon. Let's go back to that first slide. We're now in this 1800s, 1900s, we're still hanging on to this old materials technology. And it would be useful, it might give a little bit more intuition, to look at what is the mass of equipment associated with moving all of the carbon that we use today to run a coal-fired power plant.
To generate the electrical power.
And it turns out you can go into the literature, energy literature, a lot of it coming out of the Department of Energy. What I've got labeled from the bottom up are various power systems provide commercial power, PVs, Grand Coulee. We get up here to coal plants. And in the case of coal plants, mines, and trains, the height, the extent of this blue bar indicates how many tons of equipment that it takes to generate a terawatt electric year of energy. And in the case of a coal plant, it's on the order of 10 million tons of equipment. Now, nuclear reactor, and that doesn't include the coal that is burned. And I don't have that figure right off the top of my head, but I just don't have it right on the top of my head.
Right, so that's the plant itself and the equipment you need to service the plant and all that.
Yeah. Well, let's see, it takes about 3 million tons of coal to generate a 10 gigawatts. So you multiply that by 100, and that would be how much coal. So the coal is just much more massive. But this is just the equipment to do it. Okay, nuclear reactors burn almost no mass, but look at how massive the equipment itself is. That's that second, it's on the order of 30 million tons of equipment per terawatt electric year, and they've got a finite lifetime. A dam like Grand Coulee is up on the order of 80 million metric tons. Earth photovoltaics. If you had a huge array, like the one out at Nellis Air Force Base in Las Vegas, and you included the mass of batteries to let it run 2 hours after sunset, the mass of that would be on the order of 180 million tons.
So that's huge compared to even to these other really big scale things like nuclear power plants. And it's mostly the battery cost, is that right?
Well, it's a mixture of a lot of them, and this is just 2 hours. I have this a paper that I presented in China in May of 2010. Presented it to, doesn't matter. I can provide people a copy of that. But now let's go up this chart, and just the support structure for the rectennas on Earth are a tiny fraction of the coal plant and an infinitesimal fraction of the Earth photovoltaics. The active materials to pull in power is even smaller than that. And it's common materials. It's silicon, it's aluminum, plastics. It's stuff that you can build very, very quickly in large areas. The mass of the lunar production equipment using 80s technology, you can see, is so small. That's right here. And that's not counting bootstrapping from Earth. And that is all of the total mass. I'm sorry, that's the mass of the entire lunar base.
So that's if you had to bring it up from here to there?
No, it's what you build on the moon. It's what you create on the moon. The last thing, which is essentially just almost nothing, is the mass of production equipment you bring from the Earth.
Really?
And so this is where you're getting your leverage. the sun's doing all the work, and all you need on the moon are thin films, and those thin films collect the solar power and then change it into engineered microwave sunlight, which is engineered for the maximum use on the Earth.
And they last forever, basically, because there's no weather on the moon.
Well, in all of my models, I assume that you rebuild them 2 or 3 times, but primarily you'd just find better technologies to use. And it turns out the rebuilding cost is almost nothing because you've already got all the production equipment there.
Right.
Now this not last, but depending on our time, how much time do we have?
Oh, about 15 minutes.
Oh, okay. Well, we can talk slowly through this. I've tried to take a really large-scale, century-long view of our challenge. And if you went back to the year, and this graph, our table, tries to lay out business as usual through the rest of this century, doing stuff as we do now, versus changing over to the lunar power. And it's done in terms of economic cost and benefits. And if it's a plus sign, it's a benefit. So the world gross product in the year 2000 was about $40 trillion a year. If we just maintain that with a steady population increase to 10 billion people at 2050 and held it steady, the sum of that gross world product would be about $6,000 trillion.
Okay.
Now, if you think back to the, let's go down to this line, this number right here. If you think back to those PV costs, where now we're going to build a global power system to try to provide 20 terawatts of electric power. The numbers that I come up with, based partly on Mike Klimke's PhD dissertation back in the early, around 2000, the cost with 45 days of storage comes out on the order of a minus $10,000 trillion. In other words, more than the gross product of the world over that same period.
So let's just stop there for a minute.
Sure.
So what you're saying is, in order to produce power at that level, it would cost you more in that period of time than the actual gross product of the world.
Oh, that's right.
So you can't do that.
You can't do that. And that's, we looked at Solyndra, the failure, as being a management failure, and blamed in part on the decreasing PV cost from the Chinese. But when I look at the world situation, anytime you lose tax breaks or subsidies on wind or solar, production just stops. And there's a real possibility that if the cells cost you nothing, they still would not be able to power a standalone competitive system, because the whole balance of the system, the power storage, transmission lines, the uncertainties, would actually exceed what you could commercially afford to build. And
that's again because of the variability. You have to build in this storage capacity in order to have a steady power supply.
That's right. You don't have this
constant stream of sunlight being converted into constant stream of microwave beams producing a constant stream of electricity.
That's right. That's right. We need a source of industrially derived sunlight. And that's what the microwaves from the moon can be. Now, just for a cost comparison, the LSP system scaled over a 100-year period to provide 1,500 terawatt years of energy to Earth over 100 years. And Rectenna's would be about a minus $72 trillion. It'd be that much in cost. Yeah, it's trivial compared to photovoltaics. If you do bootstrapping, if you go through, and that's all your production machinery deployed from Earth, if you do bootstrapping, where you start the initial production with machines made exclusively on Earth, and then in your next stage you build 90% of those machines out of lunar material, your cost of the entire project on the would be on the order of $6.9 trillion. And the rectenna cost would be on Earth would be on the order of 77% of it. So with this approach, you're going to have an engineering, it'll be sort of like hydroelectric dam construction all over the Earth, but in the form of rectennas. And that'll be a major profit center, a major job opportunity for a generation and a half. The break even, and as I said earlier, the demonstration break even, getting to about a half a terawatt of electric power on Earth and selling at 10 cents a kilowatt hour, would be on the order of $500 billion. And another way to put this in perspective, in the Chronicle, I think it was yesterday, there was a report on this big energy meeting going on in Saudi Arabia, or Bahrain, I forget which. Worldwide cost of exploration and development for oil and natural gas in this year is projected to be $600 billion. Now, what they're doing there is more or less maintaining total global world output at the order of 85 to 90 million barrels a day. And this cost is just going to increase. If you were trying to provide 20 terawatts of electric power to the Earth and you were burning oil and natural gas to do it, you would have to burn not 85 or 90 million barrels of oil a day, but 1,000 million barrels of oil a day.
Why is that?
That's just how much you would have to burn, put into your combined cycle generators and into your power plants to get 20 terawatts out.
So you have to up it by about a factor of 10.
Yeah.
And that's how much.
And so we'll never produce that much.
We'll never produce that much, and if we did produce it and put it into the atmosphere, it would be a complete disaster.
Yeah. And so the basic difference is that you're scouring for the carbon, the fossil carbon, from all of these old oxygen atmosphere cycles. You're burning it against our present oxygen atmosphere, and it takes this massive amount of equipment to do it. Whereas with the approach described here, you do it all with thin films on the moon and thick rectenna films on the Earth.
So the impact on the environment on the Earth is essentially nil.
It's better than nil. And the reason is this last line, or not last, but the gross world product in 2050 with this approach, we'd be up to $42 trillion per terawatt electric year. And if you sum that up toward the end of the century, instead of 40 trillion, instead of 6,000 trillion dollars of gross product, I'm sorry, we would go from $40 trillion a year gross world product up to $840 trillion a year. And our combined wealth, the sum of that to the end of the century, instead of being 6,000 trillion, would be 66,000 trillion.
Right.
Now this, we talk about the 1%, how hard they work for their money, and I think some of them do, but that's wealth that they've got. Here's a way to get wealth to the entire human race.
Right.
These projections far exceed the cost of good medical care or Social Security, and it's absolutely pure sustainable wealth so that you can use energy out of this system, or you can expand the system so you could pull the industrial CO2 out of the atmosphere.
Now, there's an interesting thought.
You could clean up the upper level of our biosphere. We could actually, instead of trying to prevent damage, we could become nurturers for the biosphere we live in.
Which has to be the role that we are evolving to.
Well, it is. I mean, we're moving to cities. We're creating, most people in the developed nations, 80% or more live in cities, artificial environments. And with this pure source of electric power, these could become completely clean environments. Another interesting aspect of this is that by the time you get up to 20 terawatts of power to Earth, you can start, well before you get to that point, you can start diverting or increasing the electric output for use on the moon to support these bases and many, many other things. I guess first the moon is a research center for the, and in 40 years, the gross product, national product of the moon could be on the order of 80% of the United States today.
So the moon colony itself would have a highly productive economy.
Well, that's right.
And presumably a life. I mean, it has to be, of course, it's artificial anyway. You've got this problem of no air. But as you point out, we're living in cities which are largely artificial creations also.
That's right.
And so one could have up there people living there having a thriving, successful life, productive life.
Well, that's right. And with these, you know, like the electricity propels trains all over Europe, these power beams can propel ion drive spacecraft and facilities all throughout the inner solar system and probably out beyond, the specialized versions of them, out beyond Saturn. And so a summary is that a harvested moon would look like this. With 80s technology, you would see pairs of bases on opposite sides of the moon.
Oh, you'd actually see little dots like that?
You could with 80s technology. By the time you get to 2030s technology, those would drop from the size they are now to down to 0.2% of the lunar surface. And you would have around the moon these, I think, light reflectors that reflect sunlight down onto these bases. So as you look at the moon, you would see it. Pearls on the moon and scintillating stars going around it. And it would be changing all the time.
Right.
Based on 80s technology, draws actually on over $1 billion worth of related technology studies since the 70s. Profitable with 80s technology, much more so now. And we can, once it's implemented, we can have sustainable global prosperity, and the harvested moon will be part of our two-planet economy.
Dave Criswell, Professor Emeritus at the University of Houston, thank you for sharing with us this vision of a possible future for humanity, where our energy needs do not conflict with our environmental need and our need to become stewards of the planet rather than consumers of the planet, which is pretty much where we're at the moment.
Yeah, that's a transition we can make, and it's going to be exciting.
At a cost of less than the military budget for a year, at a cost of less than the money that's being spent now in order to go look for more fossil fuels and dig it up and transport it around and produce all the destruction that's happening. It's a kind of extraordinary possibility that I'm hoping that the people listening will take seriously and begin to work towards making happen. David, any last words you wanted to say?
Well, just good hope for the future. Here are some references. Anybody who would like to contact me can just email me at drcriswell@comcast.net. And thank you for the opportunity.
And thank you all for being with us here on Public Affairs, Public Access. We'll be back next week at the same time.